Okay, now let's move on to see what happens when we have circular cross sections, and we'll use this idea even more when we get to solids of evolution. But the region above, bounded by y equals 1/2 x plus 2 and y equals negative 1/2 x plus 2 and x equals 4, is the base of a solid if the cross section, it's not really the base in this case, it's actually going to be, makes the diameter of this. If the cross section is perpendicular to the x-axis or circles, what is the volume of the solid? Okay, so not great wording that I put in here. It should be the diameters are along here, but let's look at this. So as with all the previous videos, let's lay this out a little bit flatter to see what it will look like. So we'll get something that looks like this. Alright, those are my 3 lines. And we are cutting things perpendicular to the x-axis. So I'll just draw that right here. Oh, I went through 2. I don't like going through nice numbers integers because that might be misleading. So if I find this plane cutting through the figure along there, what I will actually get is this will be a diameter. I'll get a circle, and we can see that we actually will get a cone out of this. If I can draw a cone. So we get a cone out of here. There's the base, and as I get close to the top, I get a really small circle. Okay, so cones. We already know volumes of cones, but let's do the same process to make sure we're okay. So this right here will be the diameters of my circle, so I'll call that D. And that's the y distance along here, which is going to be very easy to find, so we know that D is going to equal the top function, 1/2 x squared plus 2, minus the bottom function, which is, did I say x squared? Sorry, 1/2 x plus 2, minus the bottom function, which is negative 1/2 x plus 2. The plus 2's will both cancel. 2 minus 2 cancels out. The negative 1/2, so minus the negative here, actually gives me a diameter equal to x. But unfortunately for us, our area formula for circles, which is what we have circles here, is in terms of the radius, and it's equal to pi times the radius squared. And the radius is half of the diameter, so that means that the radius is x over 2. So the area in terms of x is going to be pi multiplied by x over 2 squared. And I'll reduce that down a little bit right now. That's pi x squared over 4. I only need 1 pi there. Pi x squared over 4. And if you recall from much earlier, our volumes, well, we're going to actually go all the way from x equals 0 all the way up to x equals 4, because that's where our endpoints are. We can see where those two lines meet. They both have a y-intercept of 2. And so my volume will be exactly equal to the integral from 0 to 4 of the area multiplied by dx. And the area we know is pi x squared over 4. And dx we know is dx. Okay. This one's going to be much easier than the earlier problems because I can just bring out this pi over 4. It's a constant multiple. So I get pi divided by 4 multiplied by the integral from 0 to 4 of x squared dx. And now I can take an antiderivative, so that's pi divided by 4 multiplied by the antiderivative of x squared is x cubed over 3. You add 1 and divide it. I'm going to evaluate that from 0 to 4. And so that's going to equal pi over 4 multiplied by 4 cubed over 3 minus 0 cubed over 3. I actually show it pulled in here. 0 cubed over 3 is, of course, 0 over 3, which is, of course, 0. So this whole thing is gone. 4 cubed is 64 over 3. So I have pi over 4 multiplied by 64 over 3. And we can reduce this down, get 16, get 1. So I get 16 pi over 3. Which is my final answer. And I can actually check, if we look at this, we have a radius of 2, a height of 4, 1/3 pi r squared h, so 1/3 times pi times 2 squared, which is 4 times h, 16 pi over 3. We do get the right answer.